So in this section, we'll start to talk about the geometric relationships to the derivative, and the first one we'll talk about is the idea of increasing and decreasing, and so let's take a look at this definition. So let's let f be a function defined on an interval, and let x and x1 and x2 denote points in that interval. And then we say that f is increasing on the interval if f of x1 is less than f of x2 whenever x1 is less than x2. And so I often tell students that bigger x values give bigger function values. Let's take a look at a little picture of this. Okay, notice here as x gets bigger, we move off to the right, and so in this case, as x gets bigger, you see the y values get bigger, we move up, the point moves up as we move along that curve. So this function is increasing, it looks like, on the interval from 0 to 1, all right, because again, bigger x values produce bigger function values, or bigger y values. Okay, by the same token, f is decreasing on the interval if f of x1 is larger than f of x2 whenever x1 is less than x2. So in this case, bigger x values produce smaller y values or function values, and it looks like this function is decreasing, I should say, on the interval from -1 to 0, because as we move along from -1 to 0, as we move to the right, x's get bigger and the corresponding y values get smaller. As we move to the right, we go downward, okay, we're getting smaller. And then finally, and I don't have an image for this one, but you can kind of imagine, f is constant on an interval if f of x1, sorry about this, okay, is equal to f of x2 for all values of x. So if the function values are always the same, we say it's constant. Now the relationship of this to the derivative is as follows, is given in this theorem. Let x be a function that is continuous on the closed interval, differentiable on the open interval. Then if f of x is greater than 0 for all x in the open interval from a to b, f is increasing on the closed interval. Notice we get the endpoints for free here. If f of x is less than 0 on the open interval, f is decreasing, and on the closed interval, and f is 0 on the open interval, f is constant. So if f prime is positive, all right, bigger x values mean bigger y values. If f prime is negative, we're decreasing. Bigger x values mean smaller y values. And if f prime is 0, then all of the function values are the same or constant. Okay, so let's take a look at an example. Let's find the intervals on which f of x is equal to x squared times e to the x is increasing, and the intervals on which it's decreasing. So let's start out by taking the derivative. The derivative of f prime using the product rule is the derivative of the first function, 2x, times the second function, e to the x, plus the first function, x squared, times the derivative of e to the x, which is again e to the x. And notice in this expression, I can factor out, I want to compare it to 0, see where it's positive or negative, because that will tell me where it's increasing or decreasing. The function itself is increasing or decreasing. So notice here, let's see if we can factor out, I believe, an x out of each term and an e to the x. So we'll have x times e to the x times what will be left here is 2, and what will be left back here is x. So we have this expression. Notice if I look at this, if I try to find out where this is equal to 0, I'll start out that way. Where this is equal to 0, it'll be 0 when x is 0. It will be 0 when e to the x is 0, but that never happens, so this will never give us a 0. And it'll be 0 when x is -2. So let me just list those out here. All right, I'm going to put these on a number line. So at -2, it's 0. I'll put a little dotted line there, and at 0, it's 0. I'll put a little dotted line there. Now, if we look at a value of x, all right, in this region, let's say x is equal to -3. If x is negative 3, then x is negative. And e to the x, well, e to the x is always positive if you think of its graph. And x plus 2, if x is negative 3, is negative. So we'd have a negative number times a positive number times a negative number. The whole thing will be positive and will be increasing. I'll just draw a little arrow showing that we're going in that direction. As we go to the right, bigger x values produce bigger y values. Let's go between negative 2 and 0, say x is negative 1. If x is negative 1, x is negative. E to the x, as we said, was always positive. Think of its graph. And if x is negative 1, we'd have 2 minus 1, which is positive. So we have a negative times a positive times a positive. That's negative. So we must be decreasing on this interval. And finally, out here, if we go to this part of the number line, all right, x, say, is 1. If x is 1, x is positive. The next factor, e to the x, always positive. All right, and the final factor, 2x plus 1, 2 plus x is 2 plus 1, it's positive. And so the whole thing is positive. We must be increasing again. And so let's see, let's keep in mind that the only places where this thing can change signs is, since it's continuous, is when it's 0, okay? So, and it's a continuous function because it's the product of continuous functions. X is continuous, e to the x is continuous. 2 plus x is continuous. So we're increasing. I'll just abbreviate that INCR. It's increasing on this first interval, negative infinity. To remember, we get the endpoints here to negative 2. All right, and it's increasing also on 0 to infinity. And again, we get the endpoint because this is a continuous function. 0 to infinity, and decreasing, all right, on the interval, the closed interval from negative 2 to 0. Okay, I think I have a little picture of this. Let's take a look at this. And if we look at this, here's the graph of x squared e to the x. And notice if we're out to the left of negative 2, notice the positive slope, the derivative is positive, and notice as x gets bigger, the function value gets bigger. We're going upward. All right, when we get into negative 2, things change. Here's the slope. Oops, let's see. The slope is 0 here. Let me see if we can do that. The slope is 0. And now as we go from negative 2 to 0, notice the slope is negative. Bigger x's are going to produce smaller y's. Okay. And we get to the slope of 0, and here at 0 again, and then when we pass that, again, the slope is positive and bigger x values, so the derivative is positive. Bigger x values produce bigger y values. Okay, let's take one more example. Find the intervals on which f of x is equal to negative x to the 5th is increasing and decreasing. Now, if we think about that, we should think, oh, that's always decreasing because negative x to the 5th should look something like this. Well, let's take a look at this. Well, if we look at this, the derivative, we get negative 5x to the 4th. And notice, let's see, we have x to the 4th, which is always 0 or positive, all right, and negative 5, all right, which is always negative. So if we think about this, this is 0 at 0. And so to the left of 0, say at negative 1, well, negative 5 is negative. X to the 4th is positive. Negative 1 to the 4th is positive, so it's negative, we're going downward. All right, if x is bigger than 1, all right, we have negative 5 is negative. And if 1 to the 4th is 1, that's positive. So on this interval, we have a negative times a positive, that's negative, so we're going down again. So what happens here is we're decreasing, we're never increasing. On negative infinity to 0, union 0 to infinity, right? Or maybe I should say and 0 to infinity. So we're increasing on from negative infinity to infinity. If I take a bigger x any place along here, it'll produce a smaller y value. Here's a picture of this, and the picture is as follows. Notice that if we're out here to the left of 0, notice negative slope, negative derivative, and bigger x's produce smaller y's. We're decreasing. All right, and then if we go in here where the derivative is 0 here, momentarily, all right, just at that point, but then it goes on and continues to be negative again. So the derivative is negative, negative sloped, and bigger x's produce smaller y's. Okay, so that's how we test to see if a function is increasing or decreasing. We use its derivative, and this works for continuous functions that are differentiable, and where the derivative is positive, the function is increasing. Where the derivative is negative, the function is decreasing. And where the derivative is 0, the function is constant, but we don't run into that situation too often. All right, well, next we'll see the first derivative tells us if we're increasing or decreasing. What does the second derivative tell us? That we'll look at in the next video.